I'm going to go all big Clive on you now and describe the circuit of this reverse engineered solar motion sensor light. This is a 30 LED unit with no nightlight function, so it just comes on and goes off when it senses things. So on the left we have the solar panel, the source of power. I put it on the left rather than the right because it's an input. This is like the input side of the circuit, and this is the output side of the circuit as far as I'm concerned, power and output. So you've got your solar panel, which generates up to 6.1 volts in bright sunshine, and it feeds through a Schottky diode. It feeds the solar cell, and notice there's absolutely no protection, so that solar cell can get cooked in bright sunlight. So that's the first problem. The voltage of the battery goes through a 2.8 volt regulator, and there's your 2.8 volt rail, and it feeds a chip, a custom chip, and it's by the AS chip company. It's SW03BS, and it's a specially made chip for a PIR sensor and battery control sort of applications. Over here you have the PIR sensor, and and on the output of the PIR sensor you've got a pull down resistor and a capacitor. Together those form a time constant of 2.2 seconds. Another input of the SW03 is tapped off the photo cell, which gives 0 to 2 volts. It's 2 volts in the sunshine, it's 0 volts when it's dark, and that tells the chip when it's dark. There's another one here which is supposed to be an output, but it's possible that this chip has multiple modes, so it may be a voltage sensor or something like that. Not sure of that one. Over here there's a push button, which is a momentary action push button, an auto ohm resistor up to the 2.8 volts. So when you press that, it just pulls that pin up. And on the output of the chip, you've got a 1.2k resistor, no 1k resistor, sorry, glasses, and a 10k pull down driving a FET, and the FET drives the LED cob panel via a 1.8 ohm resistor. And when the LEDs are on and the battery is charged, it takes about 550 milliamps, meaning that you're going to have about 16.5 milliamps per LED, a total power of about 1.2 watts. I think that's about it really, isn't it? So, power supply, power goes down there. This chip only takes a few microamps. When that is low, it's sensitive to the PIR sensor, and when the PIR sensor senses wiggles in the infrared, it drives that pin high, and through some logic it drives that high, turns the LEDs on. There's all sorts of internal timing going on, and it's quite a clever chip because if the voltage drops too low, it turns the LEDs off, and even if the voltage comes back up, the LEDs won't turn back on until a timeout period has elapsed, and that timeout's about a day, I think. So that allows the panel to get fully charged again. As I said, this chip is capable of doing all manner of battery control functions, including overcharge and overdischarge. Now the overdischarge function seems to work. That does cut off the LED panel. If this voltage drops no, if the battery voltage drops to 2.6, below 2.6, it cuts off the solar panel. It just the LED panel. But they haven't bothered to implement the charge. You see, if they'd have put a FET there and some control circuitry and driven it from one of the outputs, probably that output actually, the thing would control the charge into the cell. So just for the sake of a couple of components, they've made us a wall light that self-destructs after 3 months, because that's about as long as it lasts in full sunlight. That cell cooks in about 3 months and goes open circuit, and yeah, it's okay, but wonky really. Okay, just for the sake of completeness, here's the printed circuit board with the PIR sensor and the little push button, and the chip, the SW03 BS chip on that end there. Sorry about the light. And I've wired this LED in place of the cob panel just to test it. The voltage from the solar panel comes in there through that's the big Schottky diode there, which feeds the battery connections. This is these are the battery connections. Red is positive, yellow is negative. That's strange, isn't it? That's the FET that drives the LEDs. That's the 1.8 ohm resistor. These are the the decoupling capacitors on either side of the regulator chip there. That's the regulator. Come on, focus. This is the PIR sensor with its components on the output driving one of these pins. This is the positive 2.8 volt rail here. Anything else of note? That's the 0 ohm resistor on the back of the push button. And that's about it really. There's not much more to say. Oh, and this particular unit has failed because the regulator has failed. It just doesn't work. There's no 2.8 volts, which is not a highly stressed component. So why would the 2.8 volt regulator fail? I mean, it's got it only supplies a few microamps. There's nothing in there that can sort of take a lot of current. But I think my theory is that the battery cooked and went open circuit, which allowed that voltage to rise to 6 volts, or over 6 volts. Now this regulator has an absolute maximum rating of 6 volts. So I think it's perhaps in the sunshine when it was being overcooked and this voltage was high, it probably exceeded the maximum rating of the regulator and popped it. Hence none of it works anymore. Anyway, I hope you enjoyed this little exploration of the LED solar sensor light. If you're wondering, this is the offending device with its guts removed. But until I can get a soldering iron capable of getting in there and replacing that teeny weeny little regulator, I don't stand much chance of repairing it, do I? Bye!